Greetings everyone, this is Mr. Mullen. Today we're going to talk about dispersion forces. This is the third type of intermolecular force. These forces are also sometimes called condensing forces because various substances at room temperature may be a liquid, a solid, or a gas. And if they've condensed into a liquid or a solid, there's some force keeping them in that state of matter. And so before we get started talking about dispersion forces, I just want to look at the simulation really fast. Here is a sample of argon. In this case, it's at a temperature where argon has actually become a solid. But at room temperature, argon is actually a gas. So I'd like you to just really quick look at these atoms of argon interacting, and you'll notice some of them are actually interacting with each other. They're actually attracted to one another. Now when you look at argon, it's just an element. It doesn't have any polarity to it. It's just a single atom. Yet somehow there's a force of attraction keeping them close to each other for some amount of time. So there actually is some force between these atoms. And if we look at oxygen, which is diatomic, if you pay really close attention, you'll also notice that some of these molecules are actually attracted to each other in a small amount of way. And so even if the molecule is not polar, we can have this force of attraction between them. And this force that you're seeing right now of attraction between these nonpolar atoms and molecules is called a dispersion force. So dispersion forces, also known as London forces, van der Waals forces, or even temporary dipole forces, are temporary forces of attraction between molecules that are caused by momentary induced dipoles. So there's a dipole being formed, a charge distribution, and it's momentary, it doesn't last very long, and this is occurring from random motion of molecules. So molecules, as you saw, were always moving. This type of force occurs between all molecules, even ones that are polar. Any molecule with electrons, in fact, can have a dispersion force. If a molecule is nonpolar, this is the only intermolecular force possible. And so oxygen, chlorine diatomic, this is a nonpolar molecule. There is no dipole. However, there is a force of attraction between molecules, and it's called a dispersion force. So this is the only force of attraction between nonpolar molecules. The more electrons that there are in a molecule, the stronger the force between the two molecules. And I'm going to show you why in a second. So I want you to imagine an atom with its electron cloud, and I want you to think of it kind of like a fishbowl full of water. At any given moment, if I rock a fishbowl back and forth, the water could be distributed at that instant at one side of the fishbowl or the other, depending on how I'm rocking it. Electrons, in a similar way, can move around the electron cloud of an atom. So at one moment in time, they could actually be on one half of a molecule or another. So what happens when molecules move rather quickly and bounce into each other, those electrons, which repel other electrons, as they get closer to each other, as atoms move closer and closer to each other, they start to repel each other. And as they repel each other, you can see those electrons moving away from each other to the opposite ends of two molecules. And when that happens, there's a temporary charge distribution. And one of the sides of the atom actually gains a temporary positive or negative charge depending upon how the electrons are shifting. So this forms a dipole, a temporary shifting of electrons to one end of the molecule. And when that happens, another molecule close by, hey, a dipole, it starts to feel the effects of the partial positive or partial negative charge. And when it feels those effects, other atoms are going to start shifting their electrons around. And what will happen is the partially negative end of the one that just ran to another molecule will actually attract the partially positive end of some other molecule and form a temporary force of attraction between those partial positive and partial negative ends. And that force of attraction is weak, but the more electrons you have, the more they can swish around. The stronger the dipole, the bigger the partial charge, and therefore the stronger the intermolecular force between the molecules. So this is a dispersion force. When you look at all three forces and rank them, spell strength there. In general, not always, but in general, hydrogen bonding is going to be the strongest. Dipole-dipole forces are going to be the next strongest, and then London dispersion forces are generally the weakest, but in some cases it can actually be greater than if the molecules are large enough. I want to show you an example of this. If you look at a periodic table for chlorine, bromine, and iodine, and you think about the phases that they exist at. Chlorine is a gas at room temp, bromine is a liquid, and iodine is actually a solid. Well, they all have diatomic molecules, they're all nonpolar. Why do they have different phases at room temperature? Well, the answer is the stronger the IMF, the greater the forces of attraction between two molecules. In an iodine, okay, if I draw out these molecules here, in terms of how many electrons they have, well, chlorine has 17 electrons, you multiply that by 2. Bromine has 35 electrons, you multiply that by 2, 70 electrons. Iodine has 53, so 106 electrons. Chlorine, 17 times 2, 74 electrons. So when I look at the amount of electrons to swish around to form these temporary dipoles, iodine has the most electrons to swish around, therefore it can have the biggest partial positive and partial negative charges, therefore it can form the strongest attraction between different molecules, so they're more likely to stick together in the solid or liquid phase rather than break free into the gas phase. And so the trend occurs why hydrogen bonding is in general the strongest and dipole-dipole the second strongest and London dispersion the weakest is the greater the difference you can have in charge, or the bigger the dipole, the more it can attract other molecules. London dispersion forces are usually weak and their dipoles don't last very long. Dipole-dipole molecules have permanent dipoles with stronger forces of attraction, and hydrogen bonding have the most polar molecules, the greatest dipoles, due to the differences in electronegativities. And the greater that dipole, or imbalance, the greater the electron cloud is distorted, and the more easily those partial charges can be felt by nearby atoms. And so going back to our simulation, it's no wonder that when we look at water, a very polar molecule, go to the liquid phase, you can actually, I'll even go to the solid phase, you can see those hydrogen bonds, those polar bonds sticking together. You can see that the hydrogens and the oxygens, the partial positive and negative, sticking together for those really polar molecules. And so they really tend to stick together well. And so water has very polar molecules. It's a very strong intermolecular force, and therefore those molecules really stick together well. And it takes a lot of energy to turn water into the gas phase as you break all those strong forces. All right, this has been a brief video on London dispersion forces, and I hope that it was helpful.